Hi kiddos, this is APES exam prep number 11. We're going to be talking about Earth's atmosphere and climate. In this first part, we'll be tackling three major questions. What is the structure and composition of the Earth's atmosphere? What characteristics of the troposphere and stratosphere most impact humans? Why? What is atmospheric circulation? And what causes the global wind patterns? What is the atmosphere? The atmosphere is just a layer of gases that surrounds the Earth that's attracted to the Earth because of Earth's gravity. As we discussed when we were talking about nutrient cycles, most of Earth's gravity is made out of nitrogen, followed by oxygen, argon, carbon dioxide, and then there's minute traces of other gases. For the most part, the Earth's atmosphere can be separated into zones or areas with specific sets of characteristics, gas concentrations, and interesting atmospheric phenomena that occur within the layer. The layer that occurs closest to the Earth is called the troposphere, followed by the stratosphere, mesosphere, thermosphere, and then there's this very, very far-reaching, very lightly associated collection of hydrogen and helium called the exosphere, which extends from our planet. So I'm going to start with the exosphere. You don't really need to know a lot about it except for that it exists. And like I said, it's a light association of hydrogen and helium that extends outside of our planet. The thermosphere, it's called that because it's a hot layer. So thermo referring to heat or temperature. If you track up these kilometers getting further and further away from the Earth, you can see that when you reach the thermosphere, the temperature starts to get very, very hot. It's been recorded that it's been even up to 1800 degrees. So that's pretty toasty. I'd find it uncomfortable. If you look at UV radiation, this is where extreme UV starts to get filtered out of our atmosphere, and so that's one other function of the thermosphere. As I'm sure you remember, meso means middle, and so the mesosphere is kind of this weird middle layer, and it is above the stratosphere and below the thermosphere. So if you've ever seen a meteor shower where you're watching shooting stars or something along those lines, what you're typically seeing is meteors burning up in the mesosphere. So the mesosphere is where the atmosphere starts to get a little thicker, and because of that, when rocks and meteors start to fall into our atmosphere, that's where they encounter enough friction where they start to burn up and you see the glowing or the falling star. The stratosphere is in between the mesosphere and the troposphere, which is closest to the Earth. The stratosphere is most known for this ozone layer, and the ozone layer is important for filtering out UV radiation. Unlike the troposphere, which gets colder as you go up the troposphere, the stratosphere actually gets warmer as you increase altitude. The troposphere, this is the layer that we call home. This is where we're going to have commercial jets. This is where we're going to see our beautiful clouds. This is where we're going to have our weather. It's the densest of the atmospheric layers because it's the closest to the Earth, and so there's the greatest attraction for those gases to the planet. Temperatures can be important because they can impact density, and as you can see that the temperature decreases as you move up the troposphere, but as you move up the stratosphere, because of the interactions with the ozone, the temperature is going to increase, and then in the mesosphere it's going to decrease before it seriously increases with the thermosphere again. You should just generally know the trends, and you should know what happens in the stratosphere and the troposphere specifically. When meteorologists are trying to get atmospheric temperatures, they usually use balloons with data collection software. And so I just wanted to give you an idea of what that might look like. So I'm going to go ahead, I'm going to launch this balloon. We're collecting data in the lower levels, right? And so those data points are going to be charted right here. If I move and I collect data points here in the troposphere a little bit higher, move it up, you're going to see that those data points are going to continue to decrease in temperature. So we're getting really low in temperature here. And if I move up, and I'm going to go ahead, I'm going to skip And there's this linear correlation, right? So we can kind of make a prediction there that there was going to be a line, and so we knew that we were going to be heading into the coldest areas of the troposphere. So now let's see what happens as we take a look at not just the troposphere, but at different areas or different regions of the atmosphere. So I'm going to go ahead, I'm going to pull this up a little bit. We'll do that. And we'll launch our balloon. Ooh, it looks like we're seeing that inversion. So let's go ahead and move our high sample up, our low sample up, and launch the balloon again. As we expected to see, so we've got the decrease in temperature as we are increasing in altitude, decreasing temperature. And then we're getting to the stratosphere. So then let's see what happens as we continue all the way to the top. So that would suggest that we've now met the stratopause and we're moving into the mesosphere. So I hope that helped illustrate the temperature variations as you move up through altitude. Something else that's important as we start to look at climate and wind is the differential heating of our planet due to its position in relation to the sun. So this can drive a lot of different systems, and I'm going to refer back to it several times. So I want you to be pretty solid on this. If you look, and this is solar radiation, you can see that this beam of light is hitting this very small area, right? But you have that same amount of energy in the northern and southern parts of the planet being distributed over much larger landmass. That means that per unit space, there's less energy to be had. This is a great video to describe differential heating and discuss its important contributions to wind and weather.
Is to understand how temperature varies across the globe. Global circulation is caused by different parts of the world heating up differently. In this first video, we will look at what causes this differential heating. The sun is our main source of heat. This heat travels to us through space in the form of radiation. This radiation is absorbed by clouds, atmospheric gases, and by the Earth's surface. Some parts of the Earth receive more of this radiation than others. The main reason for this is the curvature of the Earth. This curvature means that at higher latitudes, the radiation from the sun is spread over a much larger surface area, while the same amount of energy is much more concentrated near the equator. The radiation also travels through a greater depth of atmosphere nearer the poles in comparison to the equator. So more radiation is lost to scattering and absorption by gases and particles in the atmosphere. The tilt of the Earth also means that polar regions do not see daylight during the winter. Here the Earth is continuously sending out heat to space without any compensating incoming heat from the sun. These cold polar regions are where we see lots of snow and ice. Snow and ice, and also thick cloud, reflect a lot of the sun's radiation back into space. The reflectivity, or albedo, of the underlying surface is an important factor in determining how much of the sun's radiation is used for heating the Earth. The combined effect of all of these processes sets up a thermal gradient between the equator and the poles. In fact, the global radiation balance is such that polewards of 40 degrees latitude, the outgoing heat radiation from the Earth exceeds the incoming heat radiation from the Sun. Global circulation acts as a clever air conditioning system, redistributing the heat, stopping the equator becoming hotter and hotter and the poles becoming colder and colder, and these locations becoming uninhabitable. This circulation takes the form of 3 large atmospheric cells, which exist in both northern and southern hemispheres. Our next video shows these cells in more detail.
I love this video and how it helps to illustrate the Coriolis effect. So the Earth is always spinning, and the fluids that are moving across the Earth, like water, or you could even think of atmosphere as like a fluid layer, are going to be attracted to the movement of the Earth, even though it doesn't move at the same speed or exactly in the same way. And what that does is that can shift those cells that were just discussed earlier so that they become winds. And so as the Earth moves in one direction, so the Earth is moving in this direction, right? And the winds are moving away from the equator. It can appear that as the Earth is moving, that the winds are moving with the Earth, right? And so I just want you to be aware of what causes that, but I wanted to show you this quick little clip so that you could see exactly how that could happen even on a small scale.
Oh, hey. Like that? Yeah. Excellent. I was watching its trajectory.
Did you see the curve associated with the spin? Before we continue, I needed to talk about those cells that are formed by the differential heating on our planet. And I want you to better understand the impacts that those cells could have, not just on wind patterns, but also on climatic regions.
Different parts of the Earth heat up differently, with the equator receiving more radiative heat from the sun than the poles. And the purpose of global circulation is to redistribute this heat. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a three-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometers and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves, before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the feral cells. Unlike the other cells, the feral cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure due to the rising and descending parts of the circulation cells, giving us our climatic zones. Where air is rising, an area of low pressure is created, so these areas see much more rainfall. This is why the largest areas of rainforest are found near the equator, and why the United Kingdom has a relatively wet climate. Where air is descending, an area of high pressure forms, giving largely clear skies and little rainfall, which leads to the desert regions. But not all deserts are hot. Antarctica sits under the descending branch of the polar cell and is also classed as a desert. With more precipitation falling in the Sahara, Antarctica is...
The easiest way to understand how the Coriolis effect and those cells develop into trade winds and global wind patterns is to watch it in animation form. So I've got a short video for you right here.
In this video, you will learn about global winds. The Earth is not heated evenly. Warm air rises and creates low-pressure systems, and cold air sinks and creates high-pressure areas. This rising and falling of air creates 6 large wind sails spread out around 30 degrees around the Earth. In addition, the Coriolis Effect, which is the curving of the winds due to the Earth's rotation, impacts global wind patterns. First, polar winds. These begin near the North and South poles. Cold air in the winter sinks towards the ground, creating a high-pressure area at the poles. Winds form as they move from high-pressure area near the poles towards the low-pressure areas 30 degrees below. These winds blow from east to west. The next global winds are the Prevailing Westerlies, and they blow from west to east. These wind belts are found between 30 degrees and 60 degrees latitude in both hemispheres. The westerlies can carry moist air over the United States, producing rain and snow. Next are the trade winds. Between 30 degrees north and 30 degrees south of the equator, in an area called the horse latitudes, the Earth's rotation causes air to slant towards the equator in a southwesterly direction in the northern hemisphere and a northwesterly direction in the southern hemisphere. The Coriolis Effect, in combination with an area of high pressure, causes the trade winds to move from east to west on both sides of the equator. The trade winds of the northern and southern hemisphere meet in an area around the equator called the doldrums. In the doldrums, there is very little wind because the warm air rising creates an area of low pressure. And finally, the horse latitudes are located at about 30 degrees north and 30 degrees south. Sinking air creates an area of high pressure, and as a result, the winds at these locations are weak. These areas are called the horse latitude because, according to legend, this name was given to these areas when sailing ships carried horses from Europe to America, and when the ships were stuck in the windless area, horses were maybe thrown overboard to save drinking water for the sailors. Remember, this is just a legend. Most of the world's deserts are located around the horse latitudes because the sinking air is very dry. So there we go, the global winds of the world. Thanks for watching, and Moo Math uploads a new map.
And to finish off, can you describe the structure and composition of the Earth's atmosphere? Can you explain characteristics of the troposphere and stratosphere that are important to life on the planet? Can you explain environmental factors that result in atmospheric circulation? And can you describe the global wind patterns and explain why?